Okay, for the third part of tests of significance, we'd like to look at when something is really significant. What does that mean? So we have this letter. It looks like an A. It's Greek. It's alpha. It's our alpha level. And when something is statistically significant, we use this level to set up the point. When is it statistically significant? Okay, so we can compare the p-value with a fixed value that we regard as decisive. The decisive value of p is called the significance level known as alpha. Now remember, this p-value that we're getting is coming from our A table or the table in the back of the book, but it's something that you've been getting all along. So remember, we put it into the z-score formula. We get a z-score. Then you go over to your A table, and whether it's to the left or to the right, upper tail or lower tail, you get a p-value. If we're looking at an area in the upper tail or to the right, you're going to have to subtract that value that you get in the A table. That z-score, you find the percent, you subtract it from 1. That is your upper tail probability. That's your p-value for that particular z-score. Okay? And this decisive value of p is called our alpha level. When is enough enough? If the p-value is as small or smaller than alpha, we say that the data is statistically significant at the alpha level. Now remember, smaller, it doesn't mean to the left. All right, so if we're talking an upper tail probability here, we're looking at out at the very far on a normal distribution into the tail of the curve on the right side where it starts getting teeny tiny. That means it's getting smaller. So suppose that we have an alpha level at 5%. All right, that's our cutoff. We're not going to take any more after that. But all of a sudden we get this value out there that is 2%. Well, that's further out to the right, further into the small of the tail. Then that's significant. Our tests of significance are given a p-value. P-value is probability of the outcome that occurred just by chance, and you're used to calculating this. It's something we've been done all along, so this is not new. This is our probability that we're getting from our A table, whether we get it directly from there or if we have to subtract that value from 1. If the sample statistic falls far from the population parameter, it's good evidence against the null hypothesis. So imagine this. You have a normal distribution. You have your mean sitting in the middle. And then you go out and you get a sample and you calculate your x bar or your proportion. In this particular case, we're dealing with x bars for the next few problems. And you get your x bar, your mean of your sample. And it's ridiculously different, okay? So you check out that probability. You plug it into your z-score. All right, so you've got x bar minus mu over your standard deviation modified. And that probability is way out there. And that's good evidence that perhaps that number in the middle, that mu, is not the right number. Somebody picked it, but you know what? Our sample is way out there. Is there good evidence against the hypothesis? The alpha is the level to reject or not. So if we say that, you know what, anything beyond 5% or 1%, whatever level you pick, I'm going to reject, and you get something less than that, then you reject it. If not, you fail to reject it. We choose a significance level before we do our test. That's typical. We are announcing beforehand how much evidence against H naught we will insist on. How much can we stand before too much is too much? Since this is related to the alternative hypothesis, H alternative, we use alpha to denote it. All right, so basically an A. This is the significance level, or level of significance, okay? So this is all we're tolerating. If we have a significance level of alpha equals 5% or 0.05, we are saying that if the p-value, that value to the right in the tail, is less than 5%, we're going to conclude that H naught is false. We just can't have a value out that far if mu is really true. So somebody must be making a mistake there. Statistical significance. The p-value is more informative than the alpha level because it may be statistically significant at one level, but not at another. So suppose that you have 3%. So in this particular paragraph here says, well, let's just start with this. It says significant in the statistical sense does not mean important. Okay? It means that it's simply not likely to happen by chance. The significance level at alpha makes not likely more exact. Significance level at 0.01 is often expressed by the statement, the results were significant at p is less than 0.01. Here, P stands for the p-value that you get from your A table when you calculate your z-score and you get your probability. The p-value is more informative than a statement of significance because it allows us to assess significance at any level we choose. For example, and that's what I was alluding to earlier, a result of p equals 0.03 is significant at the 0.05 level. Okay, so we have 0.5, that's our cutoff. Oh no, our p-value is smaller than that. But if you were to happen to have it at the 1% level, well, 0.03 is greater than that. It's to the left of that. It's back towards the mu, so it's not a big deal. We'll tolerate that, and we would fail to reject our H0 at that point. So for this lesson, we're just identifying alpha levels and p-values here, so we don't have to delve further into the hypothesis test yet. If you have any questions, you can ask me later. Thank you, and I hope you enjoy this video.